Hey, hello everyone. So, do you have any questions about the last times? Okay, so maybe let us continue. Uh, so the topic is the same: initial and boundary value problems. Last time we considered the wave equation, Laplace equation or Poisson equation with a generalization to impulse equation, which is more or less the same. And one equation that we still need to study is the heat equation. And it's actually the simplest one in this family. So, heat equation. dt of u equals to Laplacian of u. Uh, boundary conditions for this equation can be the same as before. So it is either u equals to something or normal derivative of u, which can be written as a gradient, and gradient of u equals to u0. So it's boundary conditions in the coordinate space. So if it is on some r that corresponds to time times some d in rd. Boundary conditions on the boundary of this d. And we need to fix some conditions for some value of time. And the point is that well-posed problem corresponds to fixing initial conditions of 0x equals to u0 of x. So here, let me write it explicitly. So these boundary conditions are for u of t x equals to u0 of tx, or this gradient of u of tx equals to u0 of tx. So this is for x on the boundary. And this is the initial condition. So we want to study uniqueness of solutions first. So, as before, we can say that if there are two different solutions, then we take their difference and the boundary and initial conditions for this U12 are 0. So we need to study this heat equation with 0 boundary conditions, with 0 initial and boundary conditions. And to do this, let us consider, I don't know how to name it. Well, let us just consider the integral over this domain of u squared times dx, and compute a time derivative of this expression. Over this domain D, where this equation is defined. So let us differentiate it, and maybe let's put on half here. So it will equal to the integral of u times Laplacian of u ddx. And then we use these boundary conditions, namely the fact that one of these boundary conditions is satisfied, and we rewrite this integral as minus the integral of gradient of u squared dx. So this is less or equal than 0. So the right-hand side is less or equal than 0. And the left-hand side was 0, because the initial condition for u was u equals to 0. Right? So let us call this integral I of t. Well, maybe it was better to write it like this. Let us call this I of t equals to this, and then dt I of t is this. So now what we have, I of t is positive by definition, non-negative. Dt I of t is less or equal than 0. And third, since we are considering this difference, I of 0 equals to 0, because initial conditions for this difference should vanish. Therefore, this I equals to 0. Therefore, u equals to 0. So that's all. Are there any questions?
The last equal there, we are using also the fact that on the boundary our function vanishes.
Yes, either the function itself or its normal derivative. So actually, I don't think what happens if we consider some mixed boundary condition. Probably we will need to modify this integral somehow with the boundary term. But let's not consider that situation. Mm. So then there is such a parameter that decays with time. Mm. And you see that here it was important that, for example, this sign in the equation is positive. If you change the sign or instead consider not initial but final, terminal values of for this function, then we will have some problems with this proof, and there will be other problems which you will see now. Mm. So, and if you want to prove existence, for example, if you study d equals to rd, we can use the Fourier transform and solve everything for this Fourier modes. So we can say that this, in principle, we have this solution that u equals to integral to u of t and x equals to the integral over rd d dx 1 over 4 pi t to d over 2 dy, sorry. So it's just the answer. Uh, and this formula is absolutely well defined for any initial data, even if it is not non-differentiable. If it discontinuous, this function fixes any possible function. So it should be, it just needs to be integrable. If I manage to conclude this integral, then it's enough. But we can ask, this problem is definitely well posed. Mm. But there is an example of a non-well posed problem. Uh, uh, Namely, we can consider this equation with the wrong sign. Well, we can consider this equation. So either we consider a problem about a terminal value of u, or we consider the heat equation with the wrong sign. So there is some suggestion that it should correspond to insertion, to change of sign in this formula, and then we see that we immediately have some question about convergence of this integral in RD. But we also see that this change of sign of t is some bad operation, because sometimes we can get complex numbers which mean more or less nothing in here. So it's better to solve this problem going back to the Fourier transform. So if you have something like this, then we want to write u of we want to do a partial Fourier transform in coordinate space. So we will have u of t and x represented as and the integral in p over 2 pi to rd u tilde of t and x, t and k, right? So and the question is, what is the equation that is satisfied by this function u tilde of t and k? Yeah, thank you. Mhm. What does it equal to? Hmm?
I'm trying to do it. So I have to do two derivatives. So it's like I squared, so minus minus is a plus. So maybe p squared u tilde.
Yes, thanks. And the solution of this equation is u tilde of t and p equals to e to the 2 e to the t p squared times u tilde of 0 and p. So we can, and this is the initial condition. It was written somewhere there. So it's some u0. So it's e to the t p squared u0 tilde of p. So if this u0 is some function of simply exponential decay, some function that is analytic in a strip, then it becomes exponentially growing for any time greater than 0. So it means that inverse Fourier transform is non-defined already for any small time. But another situation can be that this u itself is a solution of the heat equation. In a sense, we try to run this evolution with the heat equation for some time, and then we try to reverse this evolution. So in this case, we have some guarantee that coefficients that Fourier mode of this function decay well enough, but still there will be some characteristic time at which the solution breaks. So it means that if you want to solve this inverse problem, in principle, and if you have some infinite precision, then in principle we can do this. But this solution will be defined only for some finite time. Let's say. Maybe if we consider some initial condition which is decaying even faster than exponential of minus p squared, then the solution will be defined for all possible times, but it is a kind of artificial initial condition. So summary for this is that this problem is not well posed. Mm, I don't know. So at least this naive proof breaks, but I don't know how to construct non-unique solutions of such equation. Probably it is just a problem with such kind of proof, because here it seems that this equations for the Fourier modes are well defined, but probably we can exploit somehow the fact that the solution becomes singular. I don't know. I never thought about such counterexamples. Mm. We can also ask such questions probably about Laplace equation, and I also don't know any counterexamples for uniqueness. I only know this counterexamples for the wave equation, when they look super simple. So here, probably I can try to think. Mm, not now. Mm.
This kind of reverse equation has some physical meaning, or it's just an example?
I would say not a physical meaning, but some computational meaning. It is basically the inverse problem, because for example, actually people don't solve it this way because precisely because of this problem. But in principle, we can try to approach it naively. So probably it is, if I remember correctly, it is called sometimes deconvolution. Uh, so if if we work with some maybe not physical but how to say it? So if you work with some images, for example, that have a finite number of pixels, we can have discretized versions of such equations. So we can have the heat equation with with discretized Laplacian Laplacian defined on a lattice. And so let us write it. The u of t and n, it's a Laplacian defined on a lattice of t and n. So this n is in some z mod n z to power d. Maybe we can choose the same sizes of the lattice in all directions. So z mod nz is just a circle with endpoints. So it is 0, 1, and so on, n minus 1, and it is closed at this end. So, and we have a Fourier transform in this case. So, so delta Laplacian. So in this latest Laplacian is so it is a sum of discrete derivatives u of t n plus e plus ei plus u of t n minus ei minus 2 u of t tn. Sum over all coordinates. Yes, yes. So this I just so they are not elements of vector space. They are elements of this lattice. So yeah. So there is this lattice question, and if we act with this, maybe it's a question to you. What happens with this operator if we represent u as a Fourier transform of something? So Fourier transform is given by this formula. U of t and p is 1 over n to d over 2 sum over maybe u of t and n, but I try it in this way, sum over n sum over p again in this lattice. So what kind of equation is satisfied by u tilde? So write dt of u tilde of t and p. What will we have in the right hand side? Maybe let me put here plus minus. Oh. Let me try to throw it away. But can you open the doors so oh, be careful. Oh, it's almost. But no, I think it will end soon. There. Ah, almost.
We have to decide between Filippo and.
It's come, it's come.
So, yeah. Oh, it don't look like winter. Oh, oh. So, so, do you have any ideas?
Problem is that we the problem is that we're using summon differences. So like when you, for example, at one in the I spot, you get uh, you get the same term multiplied by e to the 2 pi I over n pi, and but then they do not cancel out. You just get a sum of such terms.
But it is fine. So it will be sum of all these terms times u tilde, right?
Yeah.
Yes, it's fine. So it will be because what is written here? These are shift operators, and so and we will have three images of these shift operators. To d e to the 2 pi I over n. Maybe let us use some letter L pi p L plus e to the minus 2 pi I p L over n minus 2 times u tilde of t and p. So it's kind of shift operator instead of derivative, instead of difference operator. And now we can write it in terms of trigonometric functions. So it will be plus minus sum from L equals to 1 to d 4 sine squared of pi over n pl. U tilde of t and p. So so it is some function of a vector p, right? So and we can call it Laplacian p. So maybe it is minus sign. And
APN is the like the as translation of P, like P plus.
no, it's else component.
Okay.
So it's some element of lattice. So we have this mode of Laplacian on the lattice, and we can also see what happens when n goes to infinity. And we study such p's that p l over n to infinity, that p over n goes to 0. So in this case, this sine squared becomes so minus 4 sine of sine squares p over n PL becomes minus 4 minus 2 pi over n squared times p squared. So you can recognize something. It is the eigenvalue of a Laplace operator acting on the exponential, right? So it means that if you consider some approximation to a continuous function aside that high Fourier modes are small enough, then yes, a solution of the discrete heat equation will converge to a solution of the actual heat equation. And it can be used for some numeric approximations, and it is always done like this. So these PDs are approximated, are put on some lattice and solved this way. But also, if you have something discrete like image, and we have some Gaussian blur, which appears either naturally or was applied in some program, then we see that it can approximately be described as the solution of this discrete heat equation. So if we want to, as before, solution of this equation, which can be written absolutely explicitly as some finite sum, because we can solve this equation and then perform inverse transformation. Solution of it can be written using a discrete Green function. So u of t and n is equal to sum over some n prime z over nz power d. And and the explicit formula for this Green function is in the Fourier transform of such exponential is sum of to the 2 pi I p n over n, maybe 1 over n power d e to the t plus np. So maybe it's a question about the overall coefficient. Maybe without 1 over n, something like this. Because for t equals to 0, it should be the delta function, and the sum of delta function over the whole space should be 1. Already there is such a Green function, and now what happens here, it's just a solution of some linear equation. So this Laplace operator acts by some finite matrix, and this formula is with this G is a formula of a matrix exponential. So there is a there is some formula which is well defined for any t, and we can use it, for example, for negative t's when we want to compute the inverse transformation. And we see what is the problem. The problem is that when t is positive, then this exponential is decay for large t, and this solution converges to solution of the heat equation. But if we reverse the sign of t, it turns out that modes with a higher momentum are amplified stronger than modes with a smaller momentum, and this is something that knows about this discrete structure of a problem. So if study the discrete approximation for the non-well-posed problem, we will have something of this kind. If we wait for long enough time. But if we run it for some reasonable time, then it can. So this is called convolution for some positive time, and it add some blur to image. But if you apply it for negative time, it will be a deconvolution. It will try to reconstruct the original function. So.
Sorry, but the solution of the discrete equation, the U in the sum is like.
Oh, sorry. It's 0 and prime. Yes.
There is no continuous in general. There is no continuous analogous to the convolution. So we have. How do we do the convolution in general? Like, for example, if I know that g is wrote as the convolution of the function, how can I found the sum of these functions?
So you need to know the Fourier image of this function with which you compute the convolution, compute this convolution, just divide by this Fourier image.
I do not do that. If I don't even add that, so I cannot do that. Solve this problem.
No, actually there is some science about this in a sense how to reconstruct the original image without exact knowledge of this function, but I don't know in this science. And it's not about PDs, so probably something about this can be found in Wikipedia. So it has some application to astronomy, of course. But it is not so naive. It is some minimization problem, but I don't know this precisely. Okay, so this was about the heat equations. So we know that the only reasonable problem is to fix some initial values. And now let us go to the actual problems. And let us start with some simple example. So we will not number them. So let us just study Laplace equation on a half plane. So this half plane is so it is y, it is x, and maybe no, maybe let me number it. And the problem is the following: Laplacian of u. No, let us first specify the boundary conditions. U of x u of x0 equals to 0, and the Laplacian of u of x y equals to. Well, let us compute the green function for this problem. So there is some problem with 0 by 0. So Laplacian should equal to delta of x minus x0 delta y minus y0. And yeah, so there is boundary condition, and something else should also be fixed in this problem, because because we proved this existence and uniqueness for finite domains, but here it is some half space, and we can construct a solution of this equation with this boundary condition with and with their right hand side, and so, do you have in mind any such example? So,
function that is a 0 on the plane and
yes.
satisfies this condition.
Yes. So it solves the Laplace equation, and with this boundary condition.
So maybe just oh no, okay, no.
So we can apply some idea from the separation of variables. Namely, we can look for u of x and y equal to some f of x times g of y. Mm. Then Laplace equation will tell us that so it's called separation of variables. Laplace equation tells us that f2 prime of x plus times g of y plus f of x g 2 prime of y equals to 0. So f2 primes over f of x plus g 2 primes of y over g of y equals to 0. And since one function depends on x, another function depends on y, it means that they both should equal to some constant, but these constants are opposite. So f prime over f equals to lambda. G 2 primes over g equals to minus lambda. And how to write something of this kind? So it's fine for one function. So for example, we want this. So we can write that. So we want to solve. We want to satisfy this condition. So we write, for example, f x equals to um, sine of square root of minus lambda of minus lambda times no, g of y should either be sine of square root of lambda y. It's another option for lambda greater than 0. Or another option is to write a hyperbolic sine of square root of minus lambda times y. And in this, so in this case, f of x, so one will be a hyperbolic sine or cosine. We can write e to plus minus x square root of lambda. Yeah, and in this case it will be sine of x square root of minus lambda plus c1 plus c2 cosine of x square root of minus lambda. So is it fine? So if one solution is this, then another solution is this. Or in other words, this u of x and y is some oscillating exponential, or its friend like sine of cosine, times times growing or decaying exponential, right?
But we have two solutions. I didn't really understand why we have g of y.
Because
Sine and sine.
so one formula makes sense for positive lambdas, another for negative lambdas. So, is it fine?
Either for f of x, either exponential is good, right? So in general, I should use a linear combination, like a. Well, in the first case, like when lambda is positive. So I have g of y equal to sine of the square root of lambda times y.
Yes, you can. Yes.
Okay.
Plus c2 e to minus x square root of lambda.
Okay.
Yes, and we have both of them. But the point about this function is the following. So, for example, we are in the first situation. Then growth of this function in the y direction is limited. But if you look at the x direction, then one of these two functions go to infinity, either at plus infinity or at minus infinity. And in this situation, this g of y just goes to infinity at plus infinity. So it means that if we work with such open problems, we need to impose some conditions at infinity to get all this uniqueness results. So summarizing all this, since if you ask it to be 0, then it should be fine. So, for example, a possible boundary condition is u of x y goes to 0 when x squared plus y squared goes to infinity. But this is so this condition at infinity should be consistent with this boundary conditions, because for example, if you ask this u to be 1 on this real line, then it is inconsistent with this condition, and we should ask this u to be 1 at infinity as well. And it's not the only problem, not the only possible problem in the two-dimensional problems, because in principle, if you consider some problem with non-zero charge located in the finite domain, then green function of 2D Laplacian does not go to 0 at infinity, and it means that we need to fix not the value of u at infinity, but some asymptotics of it, which depends on this charge.
So
And
we
we'll see.
don't fix the limit, we fix the limit and the direction of the limit. Like in this case, we said that bigger circumference, the u should go to 0.
Yes.
Something like that.
In that case, we'll need to say that a function can grow logarithmically, but not faster than logarithmically. Or we can probably ask if its derivative to go to 0, and it will be enough. Okay, so are there any questions about this?
So if we ask is this condition infinity, the solution will be?
It will be unique.
Yeah, unique, and so will be the sign of square root of lambda y times that combination of sec and sine.
No, this solution, such solutions of the homogeneous equation are killed by this condition. So these are solutions of equation Laplacian of u equals to 0. They both they all go to infinity, so coefficients in front of such solutions should be 0. In the sense, we find that this all these constants in both situations should be 0. So. So, are there any other questions? But now let us solve this problem. So we want to solve these equations, and it can be done in at least two different ways. So let us first consider the simplest approach, namely the method of images. So let us study the problem with a symmetric point. So this was a plus sign, and this one will be with minus sign. And so this is x0, y0, and this will be x0 minus y0. So there are kind of two charges which appear on the right hand side. So equation which we solve is a Laplacian of u of xy is delta of x minus x0 delta of y minus y0 minus delta of x minus x0 delta of y plus y0. And the right hand side of this equation has symmetry, or better to say anti-symmetry, that if we switch, let us call this row of x, y. So this is our problem. So we know that a row of x minus y equals to minus a row of xy. And since Laplacian contains only a second derivative, this flipping sign of y does not change Laplacian. And so we can conclude that this u of x and y have the same symmetry. So u of x minus y equals to u of x, y. Minus u of x, y, sorry. And so u of x0 x0 equals to 0, right? And this second order function does not affect this equation, because we are considering it only in the upper half plane. We don't have any conditions for continuation of this function to the lower half plane. So it is just so we can write in principle anything here, but we choose this completion in such a way that a solution of this equation with this extra image charge satisfies this boundary condition. So some physical picture looks like this. There are this electric field lines, and these are and there are some equipotential surfaces like this. So if you have this system of charges, and then yx, then surface or line y equals to 0 is the equipotential surface with zero potential. And the same trick can be used in more complicated situations. So, for example, it turns out we can check that this potential surfaces will be circles. So the same approach can be used to solve some problems with circular boundaries. But it will be the next problem. And now let us solve this problem.
This approach, this technique using images. So we get a unique solution, because the problem we were playing the unique solution. So
yes.
Now we have solved that problem, imposing the symmetry between the hyperplanes.
Yes.
Okay, so that's the condition where the additional condition we're introducing.
Which additional condition?
Yeah, because before we said that in general we cannot expect unique solutions unless we impose maybe some conditions, like we talked about limits of u.
Yes.
This time we have as additional condition with symmetry, like that u can be extended on one plane by symmetry.
And it does not kill this solutions, because we can take, for example, this hyperbolic sine of minus square root of minus lambda y times any function of x, sine or cosine. It will have this symmetry property. It will solve this Laplace equation, but it doesn't go to zero at infinity.
Yeah, and so why is the solution unique? Like,
because if u goes to zero, well, maybe we should actually ask it to go to zero fast enough. So in this case, we can do that integrations by part.
okay.
So
We,
yeah.
we actually have to impose some additional conditions.
Also in general, also in the whole in the whole space to have uniqueness, we have to ask some other condition.
Yes.
Okay.
Yes.
Okay. Fine.
Yes. So we first computed the Eigen function of this equation, but which gave some solution, but did not care about uniqueness. So we have all these problems in the whole space. But usually these conditions at infinity are adjusted to a particular problem. So you try to solve it, you construct some solution, and then you ask what else should be fixed at infinity to make it unique. And there are also some other physical boundary conditions. For example, we can ask for some asymptotics at infinity. For example, this u can be some linear function. Because you see this equation, so linear functions also solve this equation. Because Laplacian of and linear function at infinity means a constant field, or if it is a hydrodynamical problem, it is constant velocity at infinity. So, so okay, let me maybe erase this. Yeah, so who knows what is the solution of this problem? Maybe up to some coefficient.
No, sì, sì, no. So maybe you can argue, you were saying you could argue that the electromagnetic field of the dipole, like in the two charges, is at every point you should do the sum of the two fields, and so maybe it goes like 1/2.
And it's two dimensions. So a given function of Laplace equation behaves like 1/r to d minus 2 from for d different from 2, and for d equals 2 is minus log of r. So actually it is minus 1/2 pi. Pi log of r. Minus probably yes. Mm. So what is it?
Yeah. Okay, so maybe it's -1/2 pi log of square root of x minus x0
Maybe
squared plus the distance.
maybe let us do like this. So it's minus x0 plus y minus y0
Okay,
square, right?
exactly.
Yes.
And then yeah, and then the same thing with a minus maybe.
Yeah, always plus here, right?
Yeah.
Yes. Yes. So it definitely solves this equation for the gain function, and it vanishes when y equals to 0, because it is just logarithm of 1. And uh, we can also compute it at in infinity. Uh, so maybe it is a little bit better to rewrite it as uh, -1/4 pi logarithm of z minus z0 absolute value squared divided by z minus z0 bar squared. It is just identical writing. And so z is x plus iy. So if you want to study it at infinity, we can write -1/4 pi logarithm of uh, 1 minus z0/z, 1 minus z0 bar over z squared. And if you expand it at infinity, it will be a -1/4 pi logarithm of so something like this squared -1/4 pi logarithm of let us write it as a product of this complex number and its conjugate. Plus something plus something. So it is -1/4 pi logarithm of 1 minus maybe 1 plus z0 minus z0 bar 1/z bar -1/z plus something. So it is minus 1 over 4 pi. Z naught minus Z naught bar, 1 over Z bar minus 1 over Z. So it is something that decays like 1 over R, and it is it is the potential of it is dipole potential, because we can say that we are studying this field at distances much higher than the distance between these two charges, so they look like a single dipole. So dipole. Actually, no. Let me think. If everything is written correctly. No, probably it is fine. Yes, it is some real expression. Okay, so are there any questions about this formula? So we know this gain function with zero boundary conditions. So now let us try to study another problem. Almost like this, but we know but now we will have zero right hand side and some boundary conditions. So the same problem was with this half plane. So now this boundary condition will be u of x 0 equals to some u boundary of x. And the Laplacian of u of x y will be 0. So we are looking for some function that has this value on the real line, y equals to 0, and solves the Laplacian equation. Do you remember approximately what kind of formula will we have for such function? So there are these different gain functions for boundary conditions, for initial conditions. So, in a sense, can we try to construct a solution of this problem using this function?
Oh yeah. Maybe. Because before we solved the problem with zero boundary condition on the plane.
Yes.
So maybe now it should be. No.
You want to solve the problem using that always the image method,
no, here, so in principle it can be solved, but in some non-trivial way we will need to take some limits probably. No, I propose to use this knowledge about relations between different gain functions. I remember we were computing some integrals like f times Laplacian of g over the domain. It was equal to some terms on the boundary, it was equal to something that follows from the equation for this gain function, and it gave us some relation between different gain functions. And the summary of this relation is the following: that gain function for this boundary problem is given by the normal derivative of gain function on the right hand side. So probably with some minus sign. So G boundary of x of x y x 0 should equal up to some sign, which we will recover now, to dy of g of x y x y x0 y0 at y equals to y0. So let us compute it. Oh, let's do this. So as you see, I don't remember this formula precisely, but it can be checked quite easily. So let us take that logarithm. We are computing dy of minus 1 over 4 pi, logarithm of x minus x 0. So it is minus 1 over 2 pi y minus y0 over so it's a derivative of the numerator, and for denominator it is 1 over 2 pi y plus y0 over oh, sorry, I wrote y equals to y equals to 0. It should be point on the boundary. Sorry. Oh, actually, I know. So y0 equals to 0, and so it was some transposition of the gain functions. So we should put here y0 derivative, and then this will be y0 minus y, and this will be y0 plus y over x minus x0 squared plus y plus y0 squared. so now put y0 equal to 0 and it gives 1 over pi y over x minus x0 squared plus y squared, x minus x0 squared. And so now the question, does this function remind you anything? No, it's not principal value. It's its friend.
It seems like the new function is dimensionally, but with y at a rate.
Green function of what? Is a hmm? Oh.
The three-dimensional one, but with y.
Oh, but you see, it doesn't have rotational symmetry. It is some function that knows about x and about y. Oh, let us look at it as a function of x with fixed value of y. So, hmm? so, hmm? What is, for example, the integral of this function in all x's? Yes, yes. So it is this one of these delta sequences. So so it can be written equivalently as 1 over pi pi I probably. So let me write on the main part. It is 1 over x minus I y minus 1 over x. No, not like this. So it can be written as I over 2 pi 1 over z minus x z minus x0 minus 1 over z bar minus x0. And it is clear that this function solves the Laplace equation between this is homomorphic, this is anti-homomorphic. So it actually solves the Laplace equation dd bar of this 1 over z minus x 0 minus 1 over z bar minus x 0. It equals to 0 for z different from x0. So if you take some function and integrate with this green function, you will definitely get something that solves Laplace equation in the upper half plane, because this function itself solves this equation. Okay, and then sorry, the sign here is plus. And also we know that since it is this delta sequence, when we go to y equals to 0, then then the solution solution coincides with this ub. So u of x and y equals to the integral dx0 from minus infinity to plus infinity uh, y over 1 over pi y over x minus x0 squared plus y squared u b of x. Oh, sorry. Of x 0. So, is it okay? So, and sorry, here it should be derivative in y0. So we verified this formula for the green function. So let us now solve. Let us now try to solve this problem in some different way. So this was a combination of these methods of images with this knowledge about different green functions. But let us try to solve this problem directly. So. So, are there any questions about this? Oh. So we want to solve this problem, and to do this, let us do partial Fourier transformation. So let us write this u of x and y equals to integral in dp over 2 pi minus infinity to plus infinity e to the ipx u tilde of p and of ip no ipx of p and y. So if we now substitute into this Laplace equation, then we will have dy squared times u of u tilde of p and y equals to what?
Should be plus u tilde, square u tilde.
Yes. And now we need to solve this equation. So in principle, there are two exponentials. So u tilde of p and y. Let us write some solution. So it will be equal to u0 of p, the Fourier mode for y equals to 0. So Fourier expansion of this function for y equals to 0. And in principle, we can add something that vanishes for y equals to 0, with some constant of p Oh, sorry, I forgot to multiply it by the exponential. Minus p squared times y. And in principle, we can write here, no, not p squared, minus py, minus absolute value of py. Mm. In principle, we can write here something that vanishes, and some constant of p, hyperbolic sine of absolute value of p, or it's just hyperbolic sine of p, y. But the problem with this term is that it is precisely from this family of solutions of the homogeneous equation that go to infinity. So this goes to infinity when y goes to infinity, and this should be excluded. So maybe let me write it like this. This constant c of p should equal to 0. So we have only this decaying exponential. So, because of this, so we see how this boundary, how these conditions at infinity work. We have some equation of second order, and usually, so if it is some finite domain, it has two boundaries. So it can be either 0 and some radius, if it is in radial coordinates, or some conditions at two boundaries. But if we work in the infinite or semi-infinite space, one of the boundaries goes to infinity, and usual condition that a function vanishes at this boundary is replaced by a condition that this function should asymptotically go to 0, which means that we should drop one of these two exponentials. In principle, we can consider some limiting problem with some boundary condition to very big radius, and this will give this condition. But we can impose it from the very beginning in such form. Mm. So this solution, and now let us write it explicitly. Let us do this inverse Fourier transform. Maybe I should first erase this. So u of x and y equals to what? It is the inverse Fourier transform. Just that formula. It is already written. Minus integral from integral from minus infinity to plus infinity dp over pi e to the minus p absolute value of y. Or minus absolute value of p times y. And then we need to substitute the Fourier transform of this initial condition. So, sorry, I forgot to write this Fourier exponential. That is ipx e to the minus absolute value of p times y. And then Fourier transform from this u0. So it is integral from minus infinity to plus infinity dx 0 e to the minus I px 0 u0 of x0. So this is u0 tilde of p. Okay, so so now there is integral in p. We need to indicate this three exponentials, and there is a integral in x0, which we will compute in the last moment, or to be precise, it will survive in the answer. On the x0, u0 of x0, integral from minus to plus infinity. So this integral, and we already computed it for many times. So who can tell the answer for this integral? Mm. And there is overall factor 1 over 2 pi here.
I think it should be x0.
Yes, thank you. I'm always writing it like this. So there are two different contributions, one from integral from 0 to plus infinity, another from 0 to minus infinity. And if you forget about this part, these two contributions are the same because function is symmetric. And so if we don't write this part, there is this integral from 0 to plus infinity, e to minus lambda t dt equals to 1 over lambda. So we can write it as a zeroth approximation and then add some correction. So
if we don't consider the first part of the exponential, we can write 2 over the.
No, let us write it separately. So there is 1 over 1 over y plus something plus 1 over y times something, right? And what kind of corrections will we have for these two integrals?
X0, x minus x0
Oh. Well, but times I, because so one integral gives we don't even care which integral gives which contribution. Maybe this one gives a contribution with minus, but it doesn't matter because there are two such contributions. One integral, another integral is this. So is integral from minus infinity to plus infinity dx0 u0 of x0 y over y squared plus x minus x x0 squared 1 over pi. So we covered the same answer that was obtained from this method of images and and relation between different green functions. Any questions about this? And it is a little bit similar to what happens with the heat equation. In that case, we could also study this kind of initial value problem, but in that case, this boundary to bulk gain function was a different approximation of the delta function. It was exponential approximation. Here it is this approximation. And of course, the gain function will always be some approximation of the delta function because we should be able to check that it is actually a solution of this boundary problem. And maybe in this last 5 minutes, I can try to show another application, another example with these images. Oh, maybe no, maybe I should not erase on this part. Well, and this application which I'm going, this example which I'm going to show now, so kind of third problem will give us some link to so-called conformal maps. Now, let us study this problem not in the half line, but in a quadrant. So we will need to write, we will need to add one image of this. So this is the original charge, and we will need, let us call it plus. We will need to add this charge with minus sign, x1, x0 minus y0. Then another charge was x minus x0 minus y0, and here was minus sign minus x0 y0. So this and this can be identified with z. This can be identified with z bar, and this can be identified with minus z, and this can be identified with minus z bar, z0. Sorry. So if we write all this and we try to write this gain function in complex coordinates, then g of z0 will be minus 1 over 2 pi times logarithm. Who can tell a logarithm of what? Logarithm of some absolute value. So what will have in the numerator and what will have in the denominator?
This is the whole gain function in terms of complex variables.
Yes.
We already write the expression like somewhere.
Well, basically, so g is minus 1 over 2 pi, logarithm of absolute value logarithm of z minus z is not.
We always like no, not the zeta z minus z0 times z plus z0.
Yes. Yes.
Over z minus z0 bar
Mhm. And yeah, so like this. So it can be written as minus 1 over 2 pi logarithm of uh, mm, abs absolute value of z of z squared minus z not squared over z squared minus z 0 squared bar. So it is minus 1 over 2 pi logarithm of some w of z minus w of z 0 over. So you see that this green function obtained by the method of images can be rewritten in this form, where w of z is z squared, right? And let us ask about this map. So what is it doing precisely? So so we have this z-plane with this quadrant. We have some w-plane. And there is this a map that sends z to w of z. So the question to you, what is the image of this line?
It should be south.
Yes, so it is here. And what is the image of this line, of the vertical line?
The other one.
Yes. Mhm. So, and if you take any line in between, they will be. So if you take some array here, then it will be somewhere here. So if you look at the argument, it is just multiplied by 2, and r is squared. So it is some homomorphic function that maps this quadrant to the upper half plane. And in this case, the answer to this green function is given by the green function on the for the upper half plane, which we already computed, combined with this conformal map from z plane to w plane. We can play the same game for some angles like pi over n. Mm, uh, we can construct these images and get some polynomial, basically polynomial z to the n minus z0 to the n. But looking at this map, we can actually write this gain function for arbitrary angle. We can simply put here z to power alpha minus z0 to power alpha, and same in the denominator. So
Yeah,
so
so
we'll
as
try.
you have n charges equidistributed, like
So you have, to succeed, you need to have two n charges. So to succeed in this image method, you need to have two n charges with interchangeable signs, like plus minus plus minus.
yeah,
So,
so for example, if I have a boundary problem in the region between two lines, the angle should be like that for a product n. and times the angle is 360. Like it should
Yes.
be a full circle.
Yes.
Okay.
But so this is a condition for which you can use this image method. And the answer will be z to the n minus z naught to the n divided by this by the same function with z naught bar. But we can think about this in different way. So we see some function that has logarithmic singularity at z equals to z naught, and it is homomorphic everywhere else, and is also zero at this boundary of this domain. So this function solves Green equation. It solves equation for the Green function, this Laplace equation on the right hand side. So it is the Green function, and it is some industrial way to construct Green functions for different domains in 2D. We simply need to know this conformal map to the upper half plane. And once we know it, we can write this expression. And it is obvious almost immediately that this way we can solve this problem for arbitrary angle. So, so if this angle is not like pi over n, this image methods does not work anymore, but conformal maps still work. We can write this answer, and it's not limited to such simple cases. There is a huge science about conformal maps with some engineering applications. And also with some relations uh, to conformal field theory and gauge theories. So there are a lot of interesting problems here. But ideologically, it looks almost like this solution of the wave equation in 1 plus 1. We have some homomorphic function that describes everything, that parameterizes different domains. So, and okay, so maybe that's all for today. Do you have any questions? So if no, then thanks for your attention. See you tomorrow.
Thank you.